Okay, in this tutorial we're talking about area, volume and measurement. Now the question I'm going through is 2022 paper 2 question 7. We're told that a candle is in the shape of a cylinder. The volume of the cylinder is 450 pi centimeters cubed and the diameter of the cylinder is 10 centimeters. Now obviously if the diameter is 10, we divide by 2, the radius must be 5. If you go to your maths tables, the formula for the volume of a cylinder is V is equal to pi r squared h. We've been told what V is, we've been told what r is, so if we sub in here, we can easily get h. So all I did was, instead of V, I sub in 450 pi, instead of r, I sub in 5. And then, to go from the first line to the second line, I divided both sides by pi. In other words, the pi's are just gone, and 5 squared is 25, so 25h equals 450. If you divide both sides by 25, your final answer is that h is 18 centimeters. Okay, in part B here, we're told that there's two different candles. One of them is a small cone, one of them is a big cone. The information we're given about the small cone is that the volume of the small cone is 12 pi centimeters cubed, and that we can refer to the height of the small cone as h. While the volume of the big cone is 150 pi centimeters cubed, and the height of the big cone is twice the height of the small cone. So if the small cone is h, the big cone is 2 times h. In terms of the radii, we're told that the big cone has a radius k times that of the small cone. So what I decided to do was to start off by referring to the radius of the small cone as r. And then the radius of the big cone is k multiplied by r. I just don't know what the k is. And based on all of this information, we have to work out what k is. So essentially we have something written down for v, h and r for the small cone and the corresponding values for the big cone. We know what the height of the big cone is relative to the small cone, and we're trying to find what the radius of the big cone is relative to the small cone. If you go to your maths tables, the volume of a cone is 1/3 pi r squared h. So let's just sub in here and see what happens. I'm going to start off with the information from the small cone. The volume would be 12 pi, and obviously 1/3 is a number, pi is a number. I'm referring to the radius of the small cone as r, so r squared will stay the same. I'm referring to the height of the small cone as h, so that's going to stay the same as well. Now what I could do now, I could divide both sides by pi, and the pi's essentially will be eliminated. Then what I could do is, to get rid of the fraction, I could multiply both sides by 3. So if I multiply both sides by 3, well, 12 multiplied by 3 is 36, and 1/3 by 3, it just cancels out, so I'm left with r squared h. So from the information on the small cone, I can say that r squared h equals 36. Now, for the moment, that's a dead end. I can't go any further there, so I'm going to sub into the information for the big cone and see how this could be useful later on. So the information I have for the big cone is that the volume is 150 pi and 1/3 pi r squared h. Well, I just write down the 1/3 and the pi. R squared, in this case for my big cone, I'm considering the radius of the cone to be kr. So if I sub in here, instead of r squared, it would be k or to be squared. And I'm referring to the height of the big cone as 2h. So instead of h, I sub in 2h. So let's just tidy this up and see what happens. First of all, I can cancel out my pi's there. What I'm also going to do on this line is multiply both sides by 3. If you multiply the left by 3, 150 by 3 is 450. If you multiply the right hand side by 3, the 1/3 and the 3 just cancel out. K r squared becomes k squared r squared, and then that's multiplied by 2 times h. So my next problem is the fact that there's a 2 here. I want to get rid of this 2, so I'm going to divide both sides by 2. If I divide the right hand side by 2, I get k squared r squared h, and if I divide the left hand side by 2, 450 divided by 2 is 225. Now I'm kind of at a dead end. There's nothing really, I can't go any further except for the fact that I have this equation. From the previous part of it, from the information on the small cone, I know that r squared h equals 36. And I have an r squared h on the right hand side of this equation. So I'm just going to do substitution here. Instead of r squared h, I'm going to sub in a 36. And now I can say that 225 equals k squared times, instead of r squared h, it's k squared times 36. Now obviously to get k squared on its own, we divide both sides by 36. And you get k squared is 225 divided by 36. If you know k squared, in order to get k on its own, you simply get the square root of both sides. The square root of 225 over 36 is 15 over 6. And if you plug 15 over 6 into your calculator, it simplifies down to 5 over 2. So your final answer there is k is equal to 5 over 2. In other words, the radius of the big cone is 2.5 times the radius of the small cone. Okay, in part C, we're given the net of a cone. The net of a cone is in the shape of the sector of a circle. If you go to page 9 in your maths tables, it tells you how to get the length of an arc along the edge of a sector. It tells you that L, the length of the arc, is 2 pi r by theta over 360 degrees. The first thing we're asked to find in part C here is that formula. It's to go from the point A to the point B. The radius is 8 centimeters and the angle at the center of the circle is 216 degrees. So you simply sub in r is 8 and theta is 216 degrees. When you plug that into your calculator, the question asks you to leave it in terms of pi, so your answer is 48 over 5 pi centimeters. So that's the first part of the question. Then you're asked to use this. It says, hence, use this to work out the radius of the cone. So you have to understand where this shape comes from, basically. The way I always think of it is like a party hat. You know the party hats that children have at birthday parties? Imagine if you just, like usually it's stapled together at one point. And if you just took that staple out, it looks like this. Essentially what you would do is you'd have this piece of cardboard. You would start here, you would wrap it around your head, and you'd staple this bit to this bit. What I'm trying to explain is that the length of the curved part of the sector here, that is the base of the cone. So imagine if I had a cone, I could write it as a two-dimensional shape like this. And I need you to understand that the circle at the base of the original cone has to be this length. The curved part of the circle is the same length as the circumference of the circular base. Notice that we've worked out the area of the length of the curved part. The length of the curved part of the net is 48 over 5 pi centimeters. We're going to use that to find the radius of this cone. So let's just wipe this out for a moment and think about that. I am trying to find the radius of the base of the cone. If you go to page 8 in your maths tables, it tells you that the circumference of a circle is equal to 2 pi r. Now, I know the circumference of this circle. The circumference of this circle is the thing that we're just after working out. It's this. So L in this case is 48 over 5 pi. That must be equal to 2 pi r. Now what I have is one equation and one unknown, so I'm going to be able to work out the radius of this circle. What I would do here is, first of all, divide both sides by pi, so the pi's are gone. Second thing I would do is simply divide both sides by 2. If I divide 48 over 5 by 2, I get 24 over 5. So the radius of this cone is 24 over 5 centimeters. And that's your final answer. That's all you needed to do. In D part I, we're told that the radius of a sphere is 2.7 centimeters. We're simply asked to get the volume of the sphere to 3 decimal places. So go to your maths tables, take down the formula for the volume of a sphere, plug it into your calculator, and you get your answer. It's 82.448 centimeters cubed. Okay, part 2 is a little bit trickier. We're dealing with the same sphere as the one from part I. We're told that the base of the sphere is cut off so that the candle can lie flat on the ground. Now obviously if you cut the base of a sphere, then the base of the new shape is a circle. There's a circular base at the bottom of this candle so that it can lie flat on the ground. We're asked to work out the new height L of this shape. They've cut off the bottom of the sphere. We need to find the new height. Let's first of all just pretend like here's where the center of the sphere is. From part I, we know the radius of the sphere is 2.7 centimeters. In other words, I know the distance from here to here is 2.7 centimeters. So really the key to this question is I just need to find the distance from the center of the sphere to the base. If I can get this distance, I'll then add 2.7, and that will tell me L, the full height of the new shape. The information we're given is that the area of the base is 5.4 centimeters squared. I can use that fact to work out the radius of the base, the distance from there to there. Remember that even though this is a two-dimensional drawing of a three-dimensional shape, so this line represents the circular base. If we were to consider just the base of this shape, it's a circle like this. And I want to work out the radius of the base. And that corresponds to the distance from here to here. I want to work out what that is. I know the area of this circle is 5.4 centimeters squared. So if I go to page 8 of my maths tables, it tells me the area of a circle A is equal to pi or squared. I know what A is. A is 5.4. So if I simply sub that in, I now have one equation and one unknown. In order to get r squared on its own, the first thing I would do is I would divide both sides by pi, and r squared is 5.4 over pi. If I know what r squared is, obviously to get r, you just get the square root of both sides. So r is the square root of 5.4 over pi. And if you plug that into your calculator, your radius works out as 1.311. In other words, the distance from the center to the edge of the base is 1.311. But more importantly, that means on the diagram given, the distance from the center of the base to the edge, that's 1.311. Now, that's really, really useful to me. Now I'm going to form a right-angled triangle. Now that I know this is 1.311, I'm easily going to be able to get the distance from the center of the sphere down to the base. Remember, the only other piece of information we have is the radius of this shape. The radius goes from the center of the sphere to the edge of the sphere. The radius of the sphere is 2.7 centimeters. That was given in D part I. Look at what I have now. We can ignore that line for the moment. What I'm trying to do here is form a right angle triangle. I know that the distance from here to here is 2.7. The distance from here to here is 1.311. So obviously if I use Pythagoras theorem, I'll be able to get this distance. Let's refer to it as x for a moment. We're going to use Pythagoras theorem. We're going to work out the value of x. So all we have to do is to sub into Pythagoras theorem to work out a value for x. I started off here, I said x squared plus 1.311 squared equals 2.7 squared. And the first few lines are fairly straightforward. You're just using your Pythagoras theorem and you end up with x is 2.36 centimeters. Now remember, we obviously know the distance from the center to the top is 2.7 centimeters. So to get a value for L, the entire length, it's going to be 2.7 centimeters plus my 2.36 centimeters. If I add them both together, I get 5.06 centimeters. But you have to be careful with your units here. The question says to leave your answer in centimeters to the nearest millimeter. So you need to remember that there are 10 millimeters in a centimeter. So if you want to leave your answer in centimeters, but be accurate to the nearest millimeter, you have to just go down one decimal place. So my final answer is 5.1 centimeters. Because 5.1 centimeters is 51 millimeters. So I have this rounded to the nearest millimeter, but it's in centimeters. Whereas if I left my answer as 5.06, well that's 50.6 millimeters. 50.6 millimeters is not to the nearest millimeter. So you round to 5.1, which is 51 millimeters. So that is to the nearest millimeter, but the unit I'm using is centimeters. Okay, in part E here, we're given a square. And there's two lines inside the square. One of them goes from the corner C to the midpoint of AB. One of them goes from the corner B to the midpoint of AD. And since E is the midpoint, we know that BE is 15, AE is 15, AF is 15, and FD is also 15. We're told as well that the two lines through the center of the square are perpendicular to each other. So all of these angles here are 90-degree angles. We're asked to use similar triangles or trigonometry to find the distance EO. Now, as far as I'm concerned, the easiest way to do this is to use similar triangles, and we're also going to use some trigonometry. The first thing we're going to do is we're going to attempt to prove that the triangle EBC and the triangle EOB are similar to each other. The biggest problem with that is the way they're written on the diagram, their orientation is different. They're not both facing the same direction. So I'm going to attempt, they're both right angle triangles, because obviously this is a 90-degree angle and this is a 90-degree angle. So I'm going to attempt to draw my two triangles like this beside each other. And essentially, I want you to just think about this. So let's take the triangle EOB. The 90-degree angle is at O. Clearly, the short distance from the 90-degree angle is OE. So I'm going to mark this as OE. And the longer distance beside the 90-degree angle is OB. So I've flipped the triangle EOB and I can draw it like that. I'm going to do the same thing now with the triangle EBC. The angle at the 90-degree, the letter at the 90-degree angle is B. And the short distance, obviously BE is only 15, while BC is 30. So the short distance is my base, that's BE is 15, and the distance from B to C is 30. It's useful to draw my triangles like this because now I can tell which sides, like I can tell which sides are the hypotenuse or which are the short base, which is the long side. So now I need to prove that these triangles are similar. And once they're similar, I'm going to be able to work out the distance OE, which is what I was asked to do. Remember that in order to prove that two triangles are similar, you have to prove they have two pairs of equal angles. So first of all, the first thing I said here was that the angle BOE equals the angle CBE, because obviously they're both 90 degrees. They're right angle triangles, and that's given in the question. The other thing that we can take, and the reason we chose these two triangles in the first place, is that they share a common angle. The angle OEB is the same as the angle BEC. If you look back at the original diagram, you can clearly see that's just the same angle. It's the angle at E is common to both of the triangles. And if you look back at any exam questions that have come up in the last 8 years on similar triangles, they nearly always involve proving that the triangles have 90-degree angles and they also have a common angle. There's very few exceptions to that. You can almost, that's the one thing you should expect when you're dealing with similar triangles. They'll have a pair of 90-degree angles and they'll have a common angle. Obviously there's other possibilities, but in the Leave Insert exam questions up to this point, usually this is what you do. Now that I've proven they have two pairs of equal angles, I can conclude that the other set of angles must be equal to each other, or in other words, that the triangles are similar. If the triangles are similar, their sides are proportional to each other. So now I can start filling in the values. So let's ignore this. The first thing you need to do is prove to the examiner that the triangles are similar. And from here it's relatively simple. I know from the question that BC is 30 centimeters. And I know from the question that BE is 15 centimeters. So that means that BE is a common side, it's in both of them. So that's 15, this is 30, this is 15. So that's all the information filled in. You should notice now that the first thing we're going to focus on here is the right hand side. I have a right angle triangle and I have two sides in it. So I'm going to use Pythagoras theorem to work out what the hypotenuse here is. Let me call it H. If we're just going to use Pythagoras, we'll work out what H is. So I've used Pythagoras theorem here. I can say that 30 squared plus 15 squared equals h squared, and it works out nice enough. It tells me the hypotenuse of the larger triangle here is 15 root 5. Now that I have that, I can answer the actual question. The question was to find the distance OE. So let's refer to this as x. Now, the key is we've proven these triangles are similar. And remember that for similar triangles, the sides are proportional to each other. In other words, the hypotenuse of this one divided by the hypotenuse of this one is equal to the base divided by the base. So that's all I have to plug in. I can say that 15, which is BE, divided by 15 root 5 is equal to the base of the small one divided by the base of the big one. And now I have one equation and one unknown, so I can easily solve to get x. All I'm going to do is I'm going to multiply both sides by 15 to get rid of the fraction. In other words, I end up with 15 by 15 over 15 root 5. Or if you just write it as that fraction multiplied by 15, it's all the same. If I plug this into my calculator, I'll get my final answer. So if you plug it into your calculator, you get your final answer, x is equal to 3 root 5 centimeters.